Okay, so today we're gonna start talking about Morse theory. So let's go. Morse theory. So I guess the first part is definition and genericity. Okay, so we've already kind of defined it before, so I'm going to be quick, but please stop me if there's something you don't understand. So let X be a manifold, possibly with boundary. And take a smooth function on X. So if you don't put a target, that always means an R-valued smooth function. So this is a smooth function of X with values in R by definition. A critical point is said to be non-degenerate if the Hessian at the point P. So what's the Hessian? Remember, the Hessian is a symmetric form. It's a symmetric bilinear form that goes from the tangent space of X times the tangent space of X to R. So if the Hessian is non-degenerate. So I think I explained what the Hessian was. It's just, there are a few different ways, but you can take the first derivative, can take the linearization of the map, and then you can take the derivative of that map, and you project it to TPX star or something. But I mean, the most direct way is just defining it by a matrix. So you can define this. Well, this is the same thing as saying that the matrix D squared of F composed with the inverse of a chart dxi, dxa, P, or at phi of P, is invertible for a chart x1 to xn. Okay? And this matrix is not invariant under change of coordinates, but the Hessian bilinear form is, provided that P is a critical point. But I think this was an exercise to show that this is well defined. This Hessian is well defined. Okay. So, any questions about this? Maybe I should write down what I said with words. So another way to define it more abstractly without using coordinates, for those who are so inclined, is to say that, well, first you have a derivative, df, which is a map that goes from X to the tangent bundle. So you can look at the linearization of this map. Well, let me call this capital df. So you can look at d of df at the point P. And that's going to go from the tangent space of X at P to the tangent space of df of P of Tx. Okay? But df of P, we're assuming it's a critical point, so df of P is equal to 0. So this is the tangent space at 0 of Tx. And the tangent space at 0 can be canonically written as the tangent space to P plus the tangent space to P. Sorry, this is a star. There's a star here. The derivative is a section of the cotangent bundle. There's a star here. And the tangent space to the bundle, to any vector bundle, at the zero section can be canonically written as a direct sum of two subspaces. So this and this. So the fiber and the tangent space. And then if you can naturally project this to the cotangent bundle, and this map from TPX to TP star of x is the Hessian. So the Hessian you can think as being the projection composed with this dp of df. So this is a map from TPX to TP star of x. And this is the same as a map from, this is canonically identified with a map from a bilinear map from TPX to R. Okay. Any questions?
I have a question.
Yeah.
How can you split the tangent of the tangent as that direct sum of TPX plus its dual space?
Well, in general, a splitting like this is called the connection on the vector bundle. But at zero, there is a unique connection. So there is a canonical way to do this.
Okay.
Yeah. So, I mean, this is equivalent to, I mean, I don't want to go into that right now because you can, for the purpose of defining a non-degenerate, a critical point, this is equivalent to this, but this is kind of connection theory. It's equivalent to choosing a horizontal section. And at zero, because you're at the zero section, there is a kind of a unique horizontal section. That's which is the same as saying that there's a unique way to project from the tangent space to the bundle to the vertical, to the fiber, which is what this pi is doing. Okay, I mean, yeah. Sorry, you can read about connections on vector bundles, and this is a comment, but you can try to do this explicitly and try to see, well, what can I project from the tangent space of E? If I have, and let's say that E is a bundle over B, and I take, the fiber over P is what I called EP. And if you take some V on the fiber of P and you look at the tangent space at V, this can be identified with the tangent space of B plus the fiber. But in general, this is not canonical. But if V is 0, then this is canonical. Okay, I won't say more about this, but this you can read any book about vector bundle connections and vector bundles. Okay. All right, but we know what the non-degenerate critical point is. You can just look at it in charts, look at the second derivative in charts, and you look whether that matrix is invertible or not. And it doesn't depend, that condition of being invertible doesn't depend on the choice of charts. Okay. So a function is Morse if all critical points, if every P critical point is non-degenerate. Okay, so those are the kinds of functions we're going to work with. And in a little bit, we're going to put some extra conditions on the Morse function, particularly if X has boundary. Okay, but before that, I'm going to prove I guess this is almost like a theorem, but it's called the Morse lemma. It's not very hard, but it's very fundamental to the theorem, which is the following. So if let P be a critical point, which is non-degenerate, non-degenerate, then there exists a chart phi around P such that the function f in this chart has a very nice expression. So it's just a constant, and then it has a quadratic term. So it's the sum of xi squared from I equals 1 to k plus the sum of xi squared from k plus 1 to n for some k. Okay, so that's what it is. And yeah, so maybe this is not completely surprising, at least at a point, if the second derivative is, if you look in charts and then the second derivative is invertible, and you know it's symmetric, then you know that, this is diagonalizable. So at least at a point, the second derivative can be diagonalizable. Okay, so that's not so surprising. But I guess what's surprising here is that not only can you do that for the second derivative, but you can actually say that the whole function is quadratic, is diagonally quadratic, if you choose a smart chart. Okay, so not surprisingly, this is some kind of version of or maybe an application of the inverse function theorem. That's kind of what allows you to do something that holds for the derivative matrix at a point, sort of locally. Okay, so let's do the proof. Let's write the proof of this. Okay, any questions about the statement first?
Eu tenho uma curiosidade, na verdade.
Sim.
Esse K, ele é um invariante para a função? Assim?
Sim, não para a função, para o ponto.
Para o ponto, tá.
Yeah, I'm gonna say more about the K after we prove this, but yeah. I mean, it's actually okay. But before we prove, I can already say, because Luciano asked. So this K is actually it's not hard to see that if you can write the function like this, then K is the dimension of the negative eigenspace of the Hessian. Right? If you write your Hessian, this is going to be, -2 in these charts. It's going to be -2, -2, and then 2, 2, 2, 2. And the dimension of the negative eigenspace is going to be it's -2. And the it's also the dimension of the negative definite part. I mean, I guess maybe I should say it like this, of HP. So yeah, so the Hessian is not really a matrix. The Hessian is a bilinear symmetric form. So it has a negative definite part. So you can think of it as a sum of a negative definite part with a positive definite part. Because it's non-degenerate, the two have to add up to n. But it's the same as the negative eigenspace of the second derivative. And even though this matrix is not well defined, the dimension of its negative eigenspace is. Okay. But anyway, it's probably just easier to look at bilinear forms, symmetric bilinear forms. Okay, so in particular, this is an invariant. It doesn't depend on the choice of charts. So this is an invariant of P. And this is called the Morse index. Okay, so now let's prove this this lemma, and then we'll talk about a bunch of examples. But let's because this proof is not very hard, and it's a nice exercise in analysis. So the proof is like this. So first of all, we fix a chart, and we can suppose that p equals 0. So we can fix a chart and suppose p equals 0. So now we translated the problem to a problem in Rn. So we now have a function that goes from an open set of 0 to R. And 0 is in U. And F and 0 is a non-degenerate critical point. Okay? So then I claim that we can write F like this. So F of x1 to xn can be written as F of 0 plus the sum of xi, xj times some function hij of x, for I, j going from 1 to n. And why is that? Well, this is basically a consequence of the fundamental theorem of calculus. So you can write f of x minus f of 0 as the integral from 0 to 1 of d dt of f of tx dt. So this is basically the sum of 0, 1. This is the gradient times x, so I can write this as the sum of df dxi at tx times xi dt. So this is, the sum over I of the integral from 0 to 1 of df dxi of tx times xi dt times of xi. And then I play the same game with this guy here. So this is going to be equal to the sum over I of the integral from 0 to 1. So this guy, but I take the difference between this and the value of this function at 0. But 0 is a non-degenerate critical point, so all the partial derivatives are 0. So this minus 0 is equal to the integral from 0 to 1 of dds of df dxi of s tx ds, and then dt, and then xi. So that's going to be equal to the sum. And now you have another chain rule here. So another gradient that I can replace with a sum. So the sum over I and j of the integral from 0 to 1, the integral from 0 to 1 of the second derivative of f dxj dxi of stx times txj xi. So it's going to be this t ds dt xi xj. Okay, here we go. So then this function here we can call hij of x. All right, and you can see this is actually symmetric. For some reason, almost every book, they don't notice that if you just do this calculation, this hij is already symmetric with respect to I and j. They kind of say that there exists such an ij and an hij, and then you can symmetrize it. But this hij that I found is already symmetric because f is C infinity. So in particular, it's C2. Okay. So now we have the function in this form. So what we have to do is we have to use the inverse function theorem to basically make what we want is to kind of make hij be the identity, or be the identity with pluses or minuses along the diagonal. Okay, so we want to make the matrix aij into something like this, plus or minus 1, plus or minus 1, etc., plus or minus 1. That's what we want. That's what we want to do. And you know, we can. It's not hard to believe that you can do it because, as I said before, you know, this Hij, well, the second derivative of f as a matrix, d2f at 0 as a matrix is just twice the matrix Hij at 0. Okay, and we know this matrix is invertible, so up to a change of coordinates, it's not hard to believe that this is going to be that we can get it to be a diagonal matrix. This is an invertible and symmetric. Okay, but let's do it explicitly. Okay, so the first step is to, we're going to change coordinates. So we're going to set, first up to a linear change of coordinates, up to composing with a linear and invertible matrix. Invertible transformation. We can assume that H110 is different from 0. Okay? So, you know, that's just because this matrix is invertible. So if I just multiply the matrix by, you know, some change of coordinates, you can assume that the first guy up there is different from 0. Okay, just by composing f with the appropriate, an appropriate linear transformation. Okay, so I can suppose that, and then now I can divide by this guy. So I can now define new coordinates, which are x1. Before that. So if x11 of 0 is different from 0, then in a sufficiently small neighborhood, of 0, the function h11 is different from 0. Okay, so because of continuity. So now I can divide by h11 of x if I'm in a sufficiently small neighborhood of 0. So now I can define x1 tilde to be the following thing. So it's going to be the square root of the absolute value of h1 of x times x1 plus x1 plus the sum of x1j over j divided by h11 of x times xj. So I define this to be x1, and then x2 is going to be x2 tilde, xj, going to be equal to xj for all j. Okay, so I have this change of coordinates, and you can check that the derivative of this at 0 is 0. Is invertible. So you can check that this is indeed a local change of coordinates. Okay, so you can just check that the derivative of this mapping at the point 0 is invertible, so by the inverse function theorem. So by the inverse function theorem, this psi of x1 to xn, which is x1 tilde, xn tilde, is a local diffeomorphism. such that psi of 0 equals 0. Okay? So now we can precompose f with the psi, f precomposed with psi inverse of x1 tilde, xn tilde. So if you just look at what f is in terms of x1 tilde and xn tilde, well, it's not very hard to see what happens. So what happens is when you take x1 tilde squared, what you get is you get the absolute value of h11 of x times x1 squared. So you're going to have sort of plus or minus x1 squared. And this plus or minus, if you want, is the sine of h11 of 0. And then what happens is in the sum, everything that has x1 will go into the x1 square, x1 tilde. Right, because when you take x1 tilde squared, then yeah, it's exactly this, because you're gonna have twice h1j times x1 xj, and the term with 1 is gonna appear twice when I equals 1 and when j equals 1. So if so basically what happens is all the terms here involving the index I or j equals 1 are going to be absorbed into x1 tilde. So you're going to end up with plus or minus x1 tilde squared plus the sum of xij, xj, xi tilde, xj tilde, and then some other function hij tilde of x. So for I and j of x tilde, I and j going from 2 to n. Okay, so that's the way to kind of get rid of all the terms with indices bigger than 1.
Can you explain again how they disappear?
Yeah. So let me look at what happens when you do x1 tilde squared. So when you do x1 tilde squared, you get the absolute value of xij of x times x1 squared plus the sum of the sine of x, sorry, this is x11, the sine of x11 of x times twice x1 xj for j equals 1 to n, and then plus some other function just of the xj's. So some quadratic term of xi xj for I and j greater than 1. Okay? And then, so, this term here doesn't really matter because it's going to be incorporated in here. And
Great.
what you have to note is that sorry, with the parentheses. So with the parentheses, there is. I want to remove this parenthesis. Okay, now it's correct. Okay, so I have some. Yeah. So okay, so what I'm claiming, so it's this plus the sum of xi xj times some whatever function of x, but with the I and j going from 2 to n. Okay, not f, some function, I don't know. H bar. Okay, so what you really want to see is this part here. No, I actually, what I want to do is I want to do hi of 0. Yeah, sorry. It's not of x. It's just of 0. Okay, otherwise that's not correct. No, I'm sorry. It's x. It's really x. Yeah. No, it is x. Because the thing is, yeah, that's right. So this guy here is going to be the sine of h11 of 0 times h11 of x. Okay, so now when you multiply this equation by the sine of h11 of 0, x1 tilde squared, then you have exactly x1 squared, and then you have plus twice the sum of h1. Oh, and I forgot to write, there was an h1j of x. So I have h1j of x times x1 xj for j equals 1 to n. Exactly. So, and then plus extra, plus the rest. But the point is that this part here is exactly what appears in the sum hij times xi xj. These are exactly the terms that appear where either I equals 1 or j equals 1.
Okay.
Okay, is that clear now?
Yes, it is. Thank you.
Okay, you're welcome. And then the point is that for I and j bigger than 1, then these terms here are exactly equal to xi tilde and j xj tilde. Okay, and I should emphasize that the dependence here is still on all the variables. It's not just on the variables bigger than 2. Okay, that's one subtle point that may be confusing the first time you see this proof. But it doesn't matter because you know when you look at the derivative matrix, it's going to have a whole line that's not necessarily 0, but it's going to be, you know, the derivative of this is going to be, you know, something like this, and then it's going to be 1 1 1 1 1 0 0. And then when you do the next iteration, you know, you do exactly the same process the next time, but now you keep the x1, you keep all the variables x3 to xn, and then for x2, you do the same thing to get rid of the terms in this quadratic sum for where either I or j equals 2. Okay, and then by induction, we obtain that f in some chart, or up to a local diffeomorphism, that f has the form f of 0, or I forgot the f of 0, plus or minus x1 squared, plus or minus x2 squared, etc., plus or minus xn squared. Okay, so there is a sign for each of these quadratic terms, and then you can condense all the negative ones. You can switch the order, and you can condense the negative ones. You can condense the positive ones, and you have exactly that expression, the expression that I mentioned in the statement. Okay, that's the end. Any questions about this? Okay, this is just really a version and being a little clever in applying the inverse function theorem.
Professor, desculpa, no passo da interação, tipo, supondo que n seja igual a 2, não teria tipo uma h que estaria no termo x2 ao quadrado? Ou
Como é que é?
Tipo, por exemplo, suponha que você vai fazer a interação, né? Aí suponha que ela acaba no próximo passo, que n é igual a 2 aqui, no seu exemplo. Não seria tipo mais ou menos x1 ao quadrado mais x2 ao quadrado, só que com uma h do lado? É tipo, como que você
Não,
queria...
porque você faz o mesmo processo, né? Você quer dizer que x1 ao quadrado mais... agora você tem um h x2 ao quadrado.
Aí como que você faz pra...
Ah, você simplesmente absorve o H, né? Você define x1 tio como sendo x1, x2 tio sendo raiz de valor absoluto de H, x2.
Tá. Agora entendi.
Se for só assim, é tranquilo, né? O problema é se, agora você vai ter um outro termo, x2, x3, e HJK, sei lá, x3 ao quadrado. Aí você vai ter que fazer a mesma coisa que você fez aqui, né? Agora, basicamente, você vai ter que fazer... Oh, fala.
Não, eu só fiquei com a impressão que, tipo, no último passo da indução, você acabaria com uma H no último termo.
Mas aí você absorve, né? Você faz mais um passo.
Tudo bem, agora ficou claro. Obrigado.
De nada. Okay. Yeah, so you need to go up to the step n. So you're going to end up, with an HNN, xn squared, and then you do one more step to eliminate the last h. So you have to do n steps, not just n minus 1. Okay, so let's look at some examples of Morse functions. So it's very common to look at submanifolds of Rn and to think of a projection to one of the R's. That's one very common way of looking at Morse functions. So let's start with looking at circles in R2. So, the easiest way is to think about a circle like this, maybe the standard circle. And the Morse function is really the height function. So I'm projecting it to the y-axis. So you see that when you do that, you have exactly two critical points. You have this one and you have this one. Okay, so those are points where the derivative is 0. You can compute this explicitly if you'd like. Maybe it is a good exercise if you are not familiar with Morse functions. And now you want to compute the indices. So it's not very hard to see that you can find a function, that this function can be locally written as x1 plus x2 squared here, plus a constant. And up here, minus x, there's just one variable. You can write it locally as x1 or x squared plus a constant. And up here, you can write it as minus x squared plus a constant. Okay, so it means that over here, how many negative terms I have? I have 0 negative terms. And here I have 1 negative term. So that means the index of this critical point is 0, and the index of this critical point is 1. Okay? If you want, we can write the function explicitly. So say that my circle is exactly the set of points x squared. Sorry, it's a little hard to write on this tablet. The set of points are x squared plus y squared equals 1. And my function goes from C to R, and it just takes x and y to y. So maybe exercise is to find these charts explicitly. So maybe I can set this an exercise. Is to find, find a Morse chart explicitly near minus 1, 0, no, 0, minus 1, and 0, 1. Okay, someone wanted to say something?
Do resultado já saiu que não depende da F?
Não, depende da F.
Não, é que você tinha dito que era um invariante do ponto.
Sim, é do ponto uma vez que você fixa a função, né? Porque isso só está definido para pontos críticos. Então, se você muda a função, o ponto não é mais crítico, né, em geral. Yeah, sorry, this is maybe if you want, you should write F here. Yeah, but definitely if you change your function, then you don't even know And then the P doesn't even have to be a critical point anymore. Yeah, yeah, it certainly depends on the function too.
O ponto é que não depende da carta, não é isso?
O ponto é que não depende da carta, exatamente.
Quando eu conseguir uma carta, eu vou mudar praticamente só essa constante aí.
Não, a constante não muda também, né? Porque a constante é a imagem do ponto. Essa constante daqui não muda.
Mas a constante depende da carta, não?
Não, essa constante é o valor da função no ponto. Essa é. Aqui, por exemplo, vai ser, para essa função específica, vai ser 1, e aqui vai ser menos 1.
É porque não tem que pré-compor com.
Mas
Não tem
eu posso
que...
transladar e aí
Pode.
vai depender então da...
Não, mas se você transladar, você não está mudando uma carta no domínio só, né? Você está mudando, você está transladando no contradomínio.
Tá.
O enunciado, né, the statement of Morse, of the Morse lemma is that you can find a chart so that you can precompose in the domain where the function has this expression. You're not changing the target at all. Yeah, so you see the f of p is here. Yeah, I mean, if you have a Morse function, you can always translate it to take, I don't know, the specific, the chosen critical point to 0 if you want. But you can't do all of them to 0 at the same time, usually. Unless you're lucky and they all have the same image.
Entendi.
Entendeu? I mean, as you can see later, we can change the Morse function. We'll see how to change the Morse function to change the value of the function. But that's something else. It's a little more complicated. Okay. So yeah, we can do that. But the point is that the constant doesn't actually matter. In a way, like the constant doesn't matter because you can translate the function. And if translating the Morse function doesn't change almost anything about the function. Yeah. But anyway, the index is given. The index is what's kind of important. Okay, so let's look at another circle in R2. Okay, so this is another circle, and I can look again at the height function, and then let's look at the critical points. We have 1, 2, 3, 4, 5, 6, 7, 8. So you see that for circles in R2, really the only thing you have when you think about this Morse function, which is a projection, is just minimum and maximum. Local minimum and local maximum. And at a local minimum, the index will be 0. And at a local maximum, the index will be 1. And that's all. There's not much variety here. Okay. Yeah. All right, so let's look at the second kind of thing that you can look, which is surfaces in R3. So let's start with your standard sphere. Now you can look again at the, well, I'm going to stop drawing this. I always, if I have a, now if I have something embedded into R3, I just look at the Morse function, which is the height function. Okay, so here it's kind of clear to see that, again, that there are only 2 critical points. And over here, the function looks like x1 squared plus x2 squared. And here it looks like minus x1 squared minus x2 squared plus constant. And the index of this critical point is 0 because I have no negative directions, and here I have two negative directions, so the index is 2. Okay. So let's think of a different embedding of the sphere. This is called the heart Morse function. Actually, let me draw a better heart. This is called the heart. Morse function. This is another embedding of this sphere into R3. And then if you look at the height function again, this is a Morse function, and it has 4 critical points. And you can check, this local minimum always has index 0. It always looks like this. A local maximum always has index 2. And here we have a saddle. So here, this is going to be index 1. So near here, the function looks like minus x1 squared plus x2 squared plus c. Okay. Right. So another example. So these are simple, but another very famous Morse function is if you look at a torus. And you can look at the torus kind of standing like this. And then you have 4 critical points. And by now, you should be able to see that this has index 0, these two have index 1, and this one has index 2. Okay. Is this clear? Any questions so far? No? I guess maybe one could ask, what about the torus that we're used to seeing? What about if you put the torus sitting on the ground? It's really hard. Okay, like this. I'm putting my torus horizontally. What about this case? Well, the problem here is that if you look at the maximum and the minimum of the function, it's actually a whole circle. So this whole circle is the maximum, and this whole circle here is the minimum of the height function. So this function, so in particular, they cannot be the derivative. The second derivative is not non-degenerate. Okay, this one way to see this is it follows from the Morse lemma that if the function has this expression, then the only critical point in this neighborhood is the point itself. So the critical points have to be isolated. They cannot form a submanifold of dimension bigger than 0. So the critical points are not isolated. So this function is not Morse. So the height function is not Morse. Okay. But anyway, it doesn't matter. You can choose another function, which is Morse, which is the height function if you put the torus vertically. And it's kind of clear to see that you can do that for any surface of any genus. And if you do that, you're going to have one index 2 critical point, one index 0 critical point, and you have a bunch of index 1 critical points. 1, 1. You have 2G index 1 critical points, where G is the genus, is the number of holes in the surface. Okay. So what about non-orientable surfaces? Can we find Morse functions on them? What do you think? Yes or no? Are you still there? You're just quiet.
Yeah. I think so, but I'm trying to think about an example.
Yeah. So for non-orientable surfaces, maybe it's a little bit harder to draw. So first of all, you know that it's harder to find embeddings into R3. And even when you find an embedding, it's a little bit, it's a little bit hard to draw. I mean, the Möbius band, you can certainly embed it into R3 and just look at a projection, and that will, if you're smart about how you do the embedding, then you can get a Morse function. But it's easier actually if you don't think only about embeddings into R3. You can draw it explicitly. So let me say that my Morse, let's start with the Möbius band. And I'm gonna, instead of embedding into R3, I'm just gonna explicitly draw the Morse function. So this is my Möbius band. What I'm gonna do is I'm gonna define the function by level curves. So I'm gonna tell you what the level curves are. So I will set, so I'm gonna say the minimum is here. And then these are, I can't quite draw, well, it's not so bad. Well, I'm gonna do my best. So I'm gonna draw a point here, which is in the middle of the circle, and then I'm gonna do okay. Actually, okay. So these are. Can you see these are my level curves, and then I have my level curves here. No. Sorry, this picture is not very good, but the point is that I can fill this with level curves that are going up, where this guy here is the minimum. And this point here, which is the same as this point here, is a saddle. Is a saddle point. So, yeah, so this is what it is. Can I try? Did I try to do that? No, I'm not going to try to draw this embedded. But anyway, you can describe this function if you want. You can even write it explicitly. So maybe an exercise, if you want to get your hands dirty and really understand, is write this function or a function like this explicitly. Write such a function explicitly. Not explicitly. I crossed the wrong. Okay. But you can kind of see. So the minimum will have index 0 and the saddle will have index 1. Okay. So now let's look at the next non-orientable surface, which is RP2. So RP2 you can think of as being, let me draw it bigger. You can think of it as being a circle where a disk where the boundary is identified like this. So similarly, you can define a Morse function that goes like this. You start from 0, and then this is a minimum. And then go like this. And then here, go like this, and this is a maximum. So in the middle is the minimum. Over here is the maximum. And here is the saddle. Okay, so you can define this explicitly too if you want. Okay, so maybe define this explicitly. And here you can, define it as a function from RP2 to R, that takes X, Y, Z to something. And I'll leave you to fill in. Okay. All right. So this is RP2, and then maybe, well, let me write another exercise, which is now for the client. I'm leaving lots of exercises this time for you to get your hands dirty with Morse functions, is to find or describe. So first you can describe like this with level curves, and if you want, you can write explicitly. So describe a Morse function on the Klein bottle with one index 0 and index 2 critical points, and 2 index 1 critical points. So you see that if you try to do this game, play this game just with level curves on the Klein bottle, and you want something to be a Morse function, so that it has to look, the neighborhood of the critical point has to look either like a minimum, maximum, or a saddle, then you will need 2 index 1 critical points. You won't be able to do it with just one saddle. You need 2 saddles, 1 minimum and 1 maximum. Okay? And then if you want, you can try to write it explicitly as a function, I don't know, of the square. Okay. Any questions about this? Okay, so before we continue, I want to introduce a couple of definitions about what adapted Morse functions are. So maybe I'll give a definition. This is not completely standard, but it's going to be the definition for today. A Morse function f so no, sorry. Actually, before this definition, let me prove a proposition, which is that, so if you have a Morse function, you could have different critical points having the same image, and that's something we would like to not have for the analysis that we're going to do. I think, yeah, we won't have a lot of time today, but next time. The proposition is the following: let X be a manifold and F a Morse function, then there exists a perturbation of F such that F tilde is still a Morse function, and whenever P and Q are different critical points, their images are different. Okay. So you can imagine, for example, here, this example that I gave of the heart, that these 2 critical points have the same image. And what I would like to assume later is that a function will always have, all the critical points are going to come at different levels. So I kind of want the pre-image of a critical value to always be 1 point. And you see why that will be good later. But anyway, like in this case, it's not hard to see that if I have this embedding of the heart, where the two points have the same image, I can just wiggle the embedding a little bit, and then they're going to have different images. Okay? And this is exactly what we need to do. So this is a very simple proposition. But let me do the proof. And the proof is simple. So first of all, since the critical points are isolated, so by the Morse lemma, the critical points are isolated. So we can let, and they have to be, because they're isolated, they have to be countable. So they're B1, B2, etc. You can have infinitely many if X is not compact. So if you have a compact manifold, so in particular, if X is compact, the number of critical points has to be less than infinity, but in any case, it doesn't matter for this proposition. But now we choose bump functions psi I supported in disjoint neighborhoods of the PIs. Okay, so if you're given they are isolated, I can choose little neighborhoods, and I can choose bump functions, okay, which are identically equal to 1, for example, near at these points and nearby, and they are so CI is equal to 1 near PI, and the support is contained in also a neighborhood of PI, small neighborhood. Okay, this is a standard thing. And now you just write F tilde as F plus the sum of epsilon I times psi I for small epsilon 1, epsilon 2, etc. So you just perturb it a little bit. And now you note that if epsilon 1 and epsilon 2 are very small, are sufficiently small, then the set of critical points, then you don't create any new critical points. So the critical points are the same as the critical points of F. And the second thing to note is that we can choose these epsilon 1 up to this infinite sequence such that the image of PI is different from the image of PJ whenever I is different from J. So the second step, you have to think a little bit about whether when you have an infinite sequence of critical points. It's not very hard, but it's maybe a little argument of countability. And you have to think about convergence and stuff, but it's pretty simple. If you don't want to think about that, you can just assume the manifold is compact and it's finite, and then it's very easy. You just choose different epsilons whenever the value of the function f coincides. Okay, but if it's infinitely many, then you have to take sequences of epsilons, and you have to make sure that they don't coincide. But it's not much harder. But anyway, it's pretty simple, and that's the end of this proposition. Okay, and you see that this is what we need. We'll need this later. So this implies, this proposition implies that if A is a critical value, of F, then we can assume that the preimage of A is a unique critical point. So this is something we're going to do a lot. Okay. And now I want to do another assumption, which really only makes sense for the case of a manifold with boundary. So let's say that, well, let's prove a proposition, I guess, and then we'll define. This is another proposition. So suppose X is a compact manifold with boundary. Then there exists a Morse function f on C infinity of a smooth function such that the critical points are all in the interior of X. Moreover, the function restricted to the boundary is equal to the maximum of F, and the function restricted to the interior is less than the maximum of F. So the idea here is that whenever I have a compact manifold with boundary, for the purposes of Morse theory, you always want to assume that the function attains its maximum on the boundary, and that there are no critical points on the boundary. So, you know, maybe something like this. So all the critical points are not on the boundary, and then and the manifold attains its maximum on the boundary. Okay, so in particular, I'm also saying that there always exists a Morse function even when X has no boundary, because I guess if the boundary is empty, then this condition this condition is vacuous. But I'm just stating that there exists a Morse function, which is something we already proved, by the way. But anyway, let's prove this proposition the way it's stated. So first of all, if the boundary of X is not empty, then there exists a color neighborhood of the boundary. So then there exists then a neighborhood of the boundary in X is diffeomorphic to minus epsilon 0 times the boundary of X. Okay? So now we can define a function. So now we can let G be a smooth function defined by, well, G of Ty equals T if Ty is in this color neighborhood. So if you're in the color neighborhood, I just define it to be this parameter here. And G of X is less than or equal to minus epsilon. Or I can define it to be, well, such that, this is not the whole definition. I can define it to be this, and I can extend it so that it's always less than or equal to minus epsilon for X not in this color neighborhood. Okay, I can't, if I just do it constant equal to minus epsilon, it's not going to be smooth. But, you know, sort of what you have is you have this color neighborhood and the function is linear. And then you can do, in a tiny little extra neighborhood, you can make it kind of go like this, and then it's constant outside this tiny neighborhood. Okay, so if you can write this down if you want. You can like extend the color neighborhood and, I don't know, take the first color neighborhood and make it linear, and then you can extend the color neighborhood and make it go down to being constant. And then you can define it to be constant everywhere else. Okay, so this is just some Just a function that has this nice property that you control it near the boundary. And then now you apply that corollary, that relative version of Thom's transversality theorem. So by a corollary of Thom's transversality theorem, we can perturb f g to a Morse function. Remember, like being Morse, we had seen this a little while ago, that it was equivalent to some transversality condition, to being transverse to S1, where we define, what S1 was in some jet space, in the jet one space, in the one jet space. So we proved that. So we can perturb, by the Thom transversality theorem, we can perturb to a Morse function so that it actually is constant near this part here. So over here, there are no critical points. So over here, we have the transversality condition. So we can perturb G to a Morse function f such that G is equal to f in the scalar neighborhood. And such that f is equal to g, I should say. And f of x is less than, well, I can't necessarily make it less than epsilon, minus epsilon, but I can make it less than epsilon over 2 for x not in this minus epsilon 0. Okay. The second condition is because we can really just perturb G, so we can make f as close to G as we want. And it's equal to minus epsilon over here. So we can make it as close to minus epsilon as we want outside in this color, and we can always get it like this. Okay, so that's this proposition. Okay, are there any questions?
Vinícius, você pode voltar um pouco para ver o statement, a afirmação, a proposição?
Sim. A proposição é que, dada uma variedade compacta com fronteira, existe uma função de Morse que tal que todos os pontos críticos estão no interior e a função atinge o máximo exatamente na fronteira.
Se ela atinge o máximo na fronteira, não seria os pontos críticos, não? O máximo não é um ponto crítico?
Não, o máximo só é o ponto crítico se você estiver no interior da variedade. It's not a critical point. I mean, only a local maximum is a critical point. But a global maximum doesn't have to be a critical point. O máximo, só o máximo local que é o máximo no interior, né, que é um ponto crítico. O máximo na fronteira não é necessariamente ponto crítico.
Tá bom.
Tá, você pode pensar num exemplo mais simples, né, que é uma função, sei lá, que faz assim. Os pontos de máximo global, né, eles não necessariamente, a derivada não se anula necessariamente. Here, I mean, yeah, I wrote it explicitly. I defined the function explicitly. So g of ty is equal to t. So the maximum this function attains is 0. It is always less than or equal to 0, and it's only 0 at exactly the boundary, 0 times the boundary. But it's not there. It's not a critical value there. Like the derivative is not 0 there.
Entendi.
Entendeu? Beleza, mais alguma dúvida? Não.
The existence,
Yeah.
the existence of Morse functions, we saw it as a consequence of Thom's transversality theorem.
Yes.
Okay.
Yeah, I mean, this is exactly, this is stronger than the existence of Morse functions, what I just proved. If you remove it, if you don't, consider this condition on the boundary, then you can just take the constant function. And then you can use Thom's transversality theorem to say that near the constant function, you can always find a Morse function.
Okay. Thank you.
You're welcome. Because being Morse, a function is Morse if and only if the first jet of the function is transverse to that submanifold S1 in the jet space.
Okay.
Yeah, so if and only if it intersects the zero section of the cotangent bundle transversely. That's what it means to be Morse.
Okay.
Yeah. So if you look at the cotangent bundle of X, here's a zero section. A function is Morse if and only if it's one jet intersects this zero section transversely. That was an exercise, something I can't remember if we did it or not, but I think we did. Yeah, so F is Morse if and only if the first jet of F intersects the zero section transversely. The zero section. Yeah. Okay. All right, so let's stop here and we'll continue tomorrow.
Sorry, can I ask another question?
Yes, yeah.
Maybe it's a little obvious, but when you made so that the critical points were different,
Yeah?
why does being epsilon sufficiently small makes sure that you don't get any new critical points?
Mas eu acho que não precisa nem escolher pequeno, não? Já que as derivadas das funções bump são zero.
Because
no, the bump function, the derivative is zero near that point, but the bump function does have like a, it's not identical. It's not always constant. So in the little area where it's changing, where the derivative is changing, right? Where the derivative is not zero, you multiply by epsilon.
Ok.
Yeah. So
okay, so you control the size of the derivative there with the
Yes.
epsilon. Okay.
yeah, because you're not so close, you're a little bit away from each critical point, then right there you're a little bit far from zero. So you just have to make the epsilon sufficiently small so that you don't hit zero.
Okay. So
Yeah.
so that you don't hit the value of the derivative of f, right?
Yeah, exactly. So you don't
Okay.
at any point in that little collar.
Okay.
Yeah.
Thank you.
Mm-hmm. You're welcome. But I mean, as you see later, you can actually do a lot more than this. We're going to be able to move the value of the function very high and very low, and we're going to play around with Morse functions quite a lot. That's coming. Okay. All right. So let's stop here.